So let's begin our set of special topics to our video lecture series on general relativity for physics students. We come to special topics A, which was planned to be more on linearized general relativity, but I feel we covered that sufficiently when we introduced the Schwarzschild metric as a preparation of the Schwarzschild metric. And so I'm just going to, I'll leave that to your supplementary lecture 11 where it's done in detail and where we covered it briefly on our way to the Schwarzschild metric. So I want to turn instead to a new topic which is very, very interesting, which is our look at rotating stars and rotating black holes. And again, we'll get into this subject gradually by starting with relatively easy things. And the easy thing to start with is slowly rotating stars, and to discuss what's called frame dragging, and discuss the Lense Thirring Precession phenomenon. Okay, so here we have we'll have a star, some mass, and it'll be rotating at a constant angular velocity, as shown in the picture. And we'll start this off by looking at the phenomena far from the mass, so that the deviation from the Minkowski metric is small, and we'll use our formalism on linearized general relativity to do that. Okay, so we'll be looking here for velocity-dependent effects, the gravity analogies to magnetism in electromagnetism. Okay, and we'll find some very strong analogies. Well, they're more than analogies because we know that special relativity implies that forces are velocity independent. Forces have to be velocity independent to satisfy a boost invariance of special relativity. We're looking at slowly rotating stars, environments where we only treat the gravitational field to first order deviations from Minkowski, and we know in those cases the problem really can be formulated and thought about as a special relativity problem. Okay, we can think of the wave h mu nu, the deviation from the Minkowski metric, as a field that's propagating in a completely flat Minkowski metric. If we have a Minkowski metric, remember, that tells us this is a problem in special relativity. Okay. Now I can also view the problem from the perspective of general relativity, and we'll be doing that here because I want to take this as a step toward strong gravity. But as we'll discuss and review, I could take a completely different approach to this, as we did in the first third of the textbook, and treat gravity-magnetism, okay, as an implication of special relativity. Okay, well let's pursue it this way. So I have my field. I've been calling it h bar alpha beta. Okay, it's the one that satisfies the wave equation. And now I'm in a situation where I have a mass of constant angular velocity. Okay, and so my fields are constant in time because the situation is stationary. It's not a static situation. Okay, that would be the mass not rotating at all. The mass is rotating, but it's rotating at a constant angular velocity, and so there's no time dependence in my fields. Okay, and so I've written that down here. Okay, the time dependence of the field, the time dependence of the source is equal to 0. Well, in that case, then my wave equation just reduces down to the Laplace equation, and that's one I know how to solve. Okay, if there's no time dependence there, it's solved by action at a distance. Okay, and each little bit of energy momentum generates a 1 upon r force, 1 upon r potential, sorry, and that contributes to h, and I get the full answer by linear superposition. Okay, so I've just written down the formula. I've done it here properly. I'm integrating over the source with a variable y, and x minus y is the distance to the observer. Okay, so now I'll take like a single star or a bunch of point particles, or what's called dust in the general relativity jargon. So I'll have a distribution of, of mass, a mass distribution, a continuous mass distribution, and the bits of it have particular four velocities as written here. Okay, and the four velocities can vary as a function of y. Well, that's certainly the case for my rotating star, okay, because I'm doing rotation, and so my velocities depend upon the distance to the axis. Okay, the outer rim of the star is moving at a higher velocity than points close to the origin or close to the axis. It's rotating around a fixed z-axis over there. So that'll be for my source, and I'm only going to be able to work the problem easily, okay, for low velocity. So I'm almost non-relativistic. My velocities divided by c are much less than 1, okay, and so my four vectors, dx by d tau, are approximately just speed of light in the zero component and the ordinary velocity in the other components, and the gamma factor is essentially equal to 1 to second order v over c, and I'm only working to lowest order in v over c. Well, to lowest order in v over c, then I can come back to my source and simplify it. The t00 component is just rho c squared, right? u0, c squared. Okay, and then t0i, for I running from 1 to 3, is just rho over here, okay, and then one of the alpha or beta is equal to 0, and the other alpha or beta is equal to I, and that's put in there. Okay, and then the higher order ones, you see, which have indices I, J, and K, I and J for 1, 2, or 3. Okay, the spatial ones, well, they're proportional to the product of a couple of velocities, 3 velocities, and so they're of order 0 in this approximation. I'm holding things to first order. I keep things to order 1 in my velocity. So I keep the 0, 0 term, which is large, the first correction, and the second corrections I drop. Okay, so there's my source. I've simplified my source, and that'll be adequate for the problem that I'll get. You see, and this will track answers to first order in the velocities. So I'll look for first order velocity dependent potentials and such, and that's what's of interest to me. Now, one of the things I look right at this, and I look at this simplification, and I notice something very interesting about it. You know, I started off with a t mu nu, which is a tensor having 10 components, okay, and that describes the gravitational source and the gravitational field completely. Now I come down here and I make these approximations, and I'm basically forgetting all of these other components. Okay, so I see I have a 0, 0 component and I have a 0i component. Well, I can say I have a 0 component and I have an I component. Okay, so I have a 4 vector. I have a 4 vector because a 0 is being held constant. I have a 4 vector. And so the source in this particular case, which is considered to be non-zero, is a 4 vector. Where have I seen a field theory with a source that's a 4 vector? Sounds like electrodynamics, doesn't it? Yes, indeed. Okay, so the formalism here is going to look a lot like electrodynamics. Okay, simply because in this approximation, the source has lost its tensor structure and it's a 4 vector. That should allow some of you to get the answers right away, because you know electricity and magnetism very well, and it's just going to be a rehash of electricity and magnetism. But I'm going to go through it using general relativity terminology, because that'll set us up for doing more difficult problems. Okay, so what do we need here? Well, we need h bar 0, 0. We need to solve this equation, okay, for the various components of h bar. Once I have h bar, then I can get h. That's the deviation of the metric from Minkowski, and I'm done. Okay, so I know what these are going to look like. They're going to look like electrodynamics, except where I used to have charge density, I now have mass density. Okay, and so I see them right here. Here's a mass current instead of a charge current generating, okay, what would have been A upper I, okay, the vector components of my electromagnetic potential, and this would, and the 0, 0's component just being my static potential, my ordinary scale of potential of electromagnetism. And I just have to relabel things appropriately. Okay, and I say that here. Bring out the resemblance to electromagnetism, just some changing in notation. Okay? Okay, and so I'm going to use that notation. So I'll replace h bar 0I by AI divided by C, where AI is this integral of the source. Okay, it's just the mass current divided by 1 upon R, and my scalar source, okay, is going to be mass density divided by the distance to the source. And in the past, we've identified already that to get the factors right, it's 4 times phi over c squared, which is h bar, and that goes through again. And in this case, we just have to put in the factor of c here. See, this is already diminished by 2 powers of c, and h bar will be diminished by a factor of c to keep my dimensions straight. So now I compute g mu nu, okay, which is eta plus h, following special topic A. Okay, we just go through the exercise of starting with h bars, okay, and going to h's using the formulas that we've used in several applications already. Most of the answers there are ones we've already gotten. We've already seen that h, okay, as opposed to h bar, h is the deviation in the metric. h00 is h11, which is h22, which is h33, which is twice the scalar potential divided by c squared. I'm just stealing that from our previous discussion, and the only new one is that h0I is ai over c. Okay, so from the equation of motion, we had that h bar 0I was ai over c, and then I just go through the machinery, you know, from h bar to h. Well, in this case, it's pretty trivial because it's off diagonal, and it just goes through without any modification at all. So that's so trivial, I just leave it to you to check it. Just put together the ingredients because they're already in the notes. Okay, then I can make the metric. So I have the metric, the metric that we call isotropic from special topics A that we discussed on our way to the Schwarzschild metric. Okay, which gives me a metric that's the lowest order when phi and a are 0 is just Minkowski, see, c squared dt squared, and then minus dx squared dy squared dz squared, and then the corrections due to the h being different from 0, putting in the 2 phi's here and the 2 phi's there, and now I have an off diagonal piece, h0I, so I have to write that into my metric. Okay, so it couples time to space, okay, and that's what I've written down here. Sum over I implied I goes from 1 to 3. So we have a new term which mixes t and x, and that reminds us of a problem that we've already done and discussed in great detail. That was the relativistic rotating reference frame, which mixed coordinates in time. Okay, so we're going to find some resemblances to that problem just because of the similar kinematics. Okay, so let's specialize to a problem where I can do everything very explicitly, and certainly that's going to be the case. Where I take a uniformly rotating sphere, okay, of radius capital R and mass m, okay, and I choose my point of observation far away so the fields are weak. Okay, well, if it's a sphere of constant charge density, of course, then I know how to do my integrals. Okay, if R is very far away, then I know I can pull this denominator outside. Okay, and then the integrals are very trivial. For phi, the source of phi is just rho d3y. That's the integral of mass density over the object. That's just the mass. Okay, and then this other integral is just the integral of the mass current over the object, and I can do that one as well. Okay, so that's what I'm setting up to do. So here, for example, is h00. Okay, and here's what it is, and then I take the little r much larger than capital R approximation, so I can pull this fellow outside the integral. Okay, and so it's just a familiar expression for me, just the 1 upon R potential. Okay, well, to evaluate the off-diagonal one, h0I, I need to work a little bit harder. I have a vector velocity inside the integral, and I want to write that in a way which expresses it as the result of a rotating star, right? So the star is rotating around, okay, and so my velocity is just the rotating angular velocity crossed into the distance of the point from the axis. So that's what I'm showing. That's what I'm showing here. Okay. So I just write u equals omega cross y. Y labels a point inside the star. I have to integrate over the star, okay, to get my total contribution. And I can write that out in Cartesian coordinates as a cross product of omega cross y. So I'll write it with my epsilon symbol, sum over L and M. You don't have to do it this way if you want to. You can just be carry on the cross product. It's just I'm going to do it this way because it's very systematic. Okay, and I can write it in Cartesian coordinates this particular way. And look, the cross product is awfully easy because omega only has a component in the 3 direction. So I only get a non-zero contribution when L is equal to 3. Okay, if L is equal to 3, then the epsilon symbol, which is fully antisymmetric, only gets a contribution when K or M are different and might be 1 or 2. So it's just hiding two terms, and they differ by sign. So it's really easy. Let's see. So I have to go to my expression for h0I, where I have the current upstairs and I have this in the denominator. Okay, and I want to simplify that in the denominator for this particular source. Okay, so it's 1 over the distance between y and x. So I'll write that as 1 over the square root of the distance written out in terms of scalars. Okay, and then this okay, and so in this particular case, x of course is large and goes out a distance r, and y is small. So I'm going to do things the first order in y. So the y squared term is dropped, and I keep this term to first order. Okay, and then to first order it's just 1 plus x dot y over r squared. Okay, just expanding it to first order. I have a minus 2 that's downstairs. I have a square root that gets rid of the 2 upstairs, and putting it upstairs flips the sign. Okay, I just, you should be good at expanding 1 plus x to any power flipped over or taken to, as you see it. Okay, and so then h0k is equal to this, okay, where here I have the 1 upon r from this, and then I have the correction, which weighs the different bits of the source differently. Okay, and so here k, l, and m are just indices going from 1, 2, and 3 to label my x, y, and z axes. Okay, so be careful when you see y to the m here. It doesn't mean power; it means index. Okay, the along the first direction, the second direction, or the third direction. Okay, the notation strikes me as a little bit ambiguous, so just keep that in mind. But you can see that here because it's on an epsilon symbol, so it's just running over the indices. Okay, and so first any of these first terms. Okay, so I'll have here 2 terms. Okay, for the 1 and for the x dot y over r squared. All the terms with the 1 give me 0. Why? Because my source has spherical symmetry, and so the weight of the mass density by any vector from the origin outward averages to 0 when I do the integral over the sphere. Okay, so that's 0 by spherical symmetry. Okay, or axial symmetry is enough actually. Okay, and so that term is going away. You see, that's why I had to do an expansion in this factor, because I have to get the first non-zero term for h0k. Okay, the leading term is 0, so it's the first correction that I need to get a non-zero contribution. as opposed to the h00 term, where I get my first leading term from just replacing x minus y by 1 over r. Okay, and so I cleaned it up. I just pick out this second term, okay, and I do the integral. Okay, so here's y with an index m, and here's y with the various indices. Okay, now the only time I'm going to get a non-zero contribution is when the index from this dot product matches the index from this fellow. So I only get the case where it's the mth component of y that contributes. So that's also the mth component of x. So I've written that down. I have the mth component of y, the mth component of y twice, so I get it squared, and then I get from this x 1x xm. Okay, and everything else is just carried along. It's a little bit tricky. Okay, so check it out as you read along in supplemental lectures. But I think I've gone through it in detail, so you see now how it works. So I have these particular integrals to do, but I see there's plenty of symmetry in my problem. First of all, I only get contributions when m is different from 3. So I'll just get contributions in the transverse direction, and it's clear that for m equal 1 or 2 that this integral is the same for m equals 1 as for m equals 2, because my system has axial symmetry. Okay, if I do this integral, okay, weighing it with the distance out from the x direction or the y direction and go all the way around, then of course I get the same values in both cases, and so I can simplify the expression like that, and that's what I've shown over here. Okay, that's what I've shown over here. Okay, and so I see I get the weighted average of the mass distribution by the square of the distance off the rotating axis. Ah, that's the moment of inertia, right? That's the definition of the moment of inertia that you know from mechanics, I sub z. So I have that in here. Okay. And then I sub z, and it's multiplied by the third component of omega. Remember, this is not omega to the third power. This means the third component of omega, as you can check as we went through the arithmetic. And so that gives me the third component, the z component, I would say, of the angular momentum. Okay, so that's what I've done here. So I've cleaned it up here. The integral here gives me iz, and I identify j in the 3 direction there. Okay, so there's omega hiding in J3. Okay, and then finally for a given k, I have the sum over the index in the index m, and I can do that. H0k gives me a contribution to the metric, just twice H0k dt dxk, right? It's just the off diagonal components in the metric. Okay, the Minkowski metric, of course, has no off diagonal components, so this is the only term you find, and then I write it out. Okay, so I get a contribution for k equals 1 and for k equals 2. I don't get a contribution for k equals 3. Okay, because that's the third axis, and I only get contributions to this integral for the transverse directions. If I set k equal to 3, then I have an epsilon symbol with 2 3's in it, and it's 0. Okay, so I get twice H01 with a x, one component, x, and then H02 with x, second component, and I write it out like that. Okay, so I've written out H like that, pull out the factors. It goes like 1 over c cubed. It's a relativistic effect, goes away in the Newtonian limit. Okay, I might write it in spherical coordinates, in which case I identify this collection as essentially the phi, the rotation angle around the z-axis, corrected by the transverse distance off the z-axis, which is sine theta r. Okay, in polar coordinates, right? So sometimes in some of the books you'll see it written in that fashion, and as is my habit, I forgot the sine squared theta here. Okay, but that should be there. I'm going to be using actually the Cartesian expression, so so my little goof there doesn't carry through. Here you see I've written it out here and I've written it properly. And I use, instead of x1 and x2, I'll use x and y over here because I think it's clearer notation. Okay, so here, first terms, last terms, what I'm used to, that's the, that's the metric that I know from static problems. And now from stationary problems, I get a coupling of space and time proportional to the angular momentum, the Newton's gravitational constant. It falls like r cubed, okay, and falls like c cubed. Okay. Okay. So let's see what it does. Okay. It mixes time and space. Okay. It represents rotation. Let's see what rotational effects it has, and the simplest effect to look for is to look for a kind of a magnetic moment, the analog of a magnetic moment precession in a magnetic field. Okay, the off-diagonal term is proportional to J and M. It is magnetic, comes from the current carried by the spinning mass. So what we'll do is we'll imagine being out in outer space with a star somewhere rotating with a angular velocity omega, and I'm going to take a gyroscope, okay, which is along the axis of rotation, pointing in the transverse direction, and let it drop. Okay, and then the issue is, does it spin? Okay, Newton would say, of course it doesn't spin. The gravitational potential due to a mass is unaffected by its rotation. Okay, okay. We're getting indications that that's probably not true, since we got a change in the metric, a coupling between time and transverse coordinates. So this is a good way to check and see what the physical implications of that rotation are. Is the gyroscope going to start spinning, rotating in this environment? So I take the spin of the gyroscope and I align it in the transverse direction, and I drop the gyroscope down and see what happens. Okay. According to Newton, the gyroscope will maintain its orientation as it falls in the gravitational field. Okay, right? Right? That's certainly the case. There's no preference left or right. In Newton's world, there's no preference left and right, because that rotating star generates the same potential regardless of its omega. Okay, not so in relativity. Okay. And so we have a chance for finding a non-trivial result. Okay, so the gyroscope falls, and the gyroscope carries its spin, and the spin is falling in a gravitational field. So it parallel transports. Okay, so it parallel transports, as we've discussed in our other applications. Okay, so I just pull out my trusty parallel transport equation, okay, and there you have it. That should give me the time development of the spin. Tau is the proper time, let's say, for the body of the gyroscope as it falls down. Gammas are my Christoffel symbols. S is my spin. I'm just writing out parallel transport for S. S should parallel transport as it moves in this quote force-free environment in curved space. Okay, and it follows the curve x beta, whose tangent is u beta. Okay, so it's falling directly down, and so its velocity, 4 vector, is just u0, nothing in the transverse direction, something in the 3 direction, naturally it's falling, and my spin only has components in the x and y direction. I don't know what they are. That's what I want to find out. I notice, of course, that my spin 4 vector dotted into my velocity 4 vector is equal to 0. Okay. Well, okay. Just take the dot product. Well, you just go to this is a dot product. It's an invariant. Jump to the freely falling frame where the particle is at rest. Then u only has a time component, and the spin only has spatial components, so the 0 is trivial. And u dot s is conserved. Okay, and that's of course what I expect. Okay, s is parallel being parallel transported along the geodesic of the particle, and we proved, we showed, both in differential geometry and in this course, that under those circumstances, the dot product of a parallel transported vector with the tangent to the curve, which is also parallel transporting, is conserved. And see explicit. There's an easy example of all that. Okay, so there you go. So now I know how to parameterize my variables, and now I need finally my Christoffel symbols for linear gravity, and we've done that already in several occasions. Okay, so I've written it out here in general. Okay, and then I've cleaned it up. Okay, the gradients of G are proportional to H. Okay, and so the raising and lowering is done by the zeroth order term in the metric eta, because corrections to that would give me contributions to Christoffel symbol at second order in H, and I'm only working for first order in H. And that's just another illustration of the fact, that linear gravity is a problem in Minkowski space. Okay. We've specialized in non-relativistic motion. Okay, again, just to make my life easy. So the gyroscope is falling, but it's not falling relativistically. It's falling with a modest velocity. So I'll be able to take U3 essentially to 0 compared to U0, which is C. Okay, to leading order. So again, to leading order in the 4 velocity of the gyroscope. Okay. So then I write out my parallel transport equations, and here they are written out completely. Okay, I've written them out for U only having a 0th component, so that simplifies the Christoffel indices, and then S only has transverse components, so again that simplifies the indices, and those are the only combinations I get. Okay, then finally I have the formula for the Christoffel symbols. Okay, and I can plug into them the H's that I know, and take the derivatives. And here are the 2 leading terms I get. Gamma, I get gamma upper 1, lower 2, 0, and I get gamma 2, lower 1, 0 over here, and gamma 1, 2, 0 over there. Okay, and the other ones, the other 2 Christoffel symbols are smaller by a factor of C. Okay, so they're dropped. Okay, and then I put these Christoffel symbols into the formula, drop the irrelevant ones, and here are my formulas. Okay, well, I know I've studied precession in elementary physics, and I've seen it in electrodynamics, and lo and behold, there it is, classical precession. Okay, so we recognize this. See, S1 is coupled to S2, S2 is coupled to S1, minus sign here, a plus sign there. It's just that d by d tau of S is equal to a precession angular velocity crossed with S, and I read off what it is. I read off the magnitude here, okay, and I see it's pointing in the K, in the 3 direction like that. Okay, so I see that that's the end of my problem. I could write down spin, with the initial conditions and then sinusoidal variation with omega sub pt, but I don't want to bother with that because I'm so familiar with this formula from elementary physics, that the spin precesses around the z-axis with an angular velocity of omega p, where omega p is 2gj over c squared r cubed. Okay. So it precesses faster as I get closer in, and that's certainly as expected. The field is bigger there. This is called the Lense Thirring effect. Okay, and it was calculated in 1919, rather early after the discovery of general relativity. It's been measured by NASA by looking at gyroscopes orbiting the Earth, and verified to about 10%. There are other geodesic precession. Well, there are other precessions that you can find in general relativity. Okay, this is one that's special for rotating stars. Okay, and it's a linear effect. Okay, it's not a nonlinear general relativity effect. Okay, but we could take a star which is not rotating and orbit a gyroscope around it. We would also find a precession for it as well. That's called geodesic precession. Okay, and it's a much larger effect okay, than this one, and that was also measured in NASA's experimental probe B. And I give you the website for that in the notes. So there you go. We derived this famous lens Thirring effect, and okay, and it's quite interesting, an effect of a type of what we call gravity magnetism. Okay, so we'll continue on with gravity magnetism next time. Okay, and see more such effects. Okay, so till then.